Hello everyone, I'm Anil Bharate from Department of Computer Science and Engineering, BLDA CET, Vijaypur. In this video, I'm going to explain the concepts from DMS such as converse, inverse and contrapositive and logical implication as well. Now, coming to one condition, P conditional Q. If we have this conditional, then there are three possibilities for this conditional. We may have converse of this condition, inverse of this condition and contrapositive of this conditional. Now consider this conditional P conditional Q, then Q conditional P is nothing but converse of P conditional Q. So Q conditional P is converse of P conditional Q. Now similarly, or in other way, not P conditional not Q is inverse of conditional P conditional Q, and not Q conditional not P is called as contrapositive of P conditional Q. So these are the three statements. I'll repeat. If there is a conditional P conditional Q, then Q conditional P is called as converse of P conditional Q. Then not P conditional not Q is called as inverse. Not Q conditional not P is called as contrapositive of this. So the first one is converse, means you can say just reverse this, it will be a converse. Then if you apply negative for this conditional, both sides, negative negation of P, conditional negation of Q, it becomes inverse. And if you again reverse this part, it will become contrapositive. Now let us consider one example as P. 2 is an integer, then one more proposition Q. 9 is multiple of 3. These are the two. Now here, this is the conditional. P conditional Q means what? If 2 is an integer, then 9 is multiple of 3. Now there are three possibilities. We may write converse, inverse and contrapositive for these three statements. Let us see. What is converse of P conditional Q first? So Q conditional P is the converse. Now how I can represent this statement in terms of these statements? Q means 9 is multiple of 3. So right, 9 is multiple of 3. Then what? Then P. P means 2 is an integer. 2 is an integer. So this is converse of the given P conditional Q. Now what is inverse? Not P conditional not Q is the inverse. Now how I can write this statement? Not P means 2 is an integer, not P is 2 is not an integer. So right, let me write 2 is not an integer. Sorry, if should be added here first. If 2 is not integer, then what is Q? 9 is multiple of 3, but not Q means 9 is not multiple of Q. Then 9 is not multiple of 3. So this is the inverse of given statement or given conditional. And what is contrapositive? Contrapositive is nothing but not Q, then not P. How can I write this statement? Not Q means 9 is not multiple of 3. Say if 9 is not multiple of 3, then not P. Not P means 2 is not integer. Then 2 is not an integer. So this is how we can write the converse, inverse and contrapositive of a given conditional. Now next, we will consider truth table for all these. So I have considered here P, Q, then we have not P, not Q. Then here, see, P conditional Q, its converse, its inverse and its contrapositive. All possibilities we have considered over here. Now let me write not p values. Not p means negation of all these. So instead of 0 0 1 1 it will be 1 1 0 0. Not q means instead of 0 1 0 1 it will be 1 0 1 0. P conditional q means first value should be 1, next value should be 0, then only 0, otherwise all values will be 1. So if there is first input is 0, straight away you should write it as 1. See again 1. Now first input is 1, second input is 0, then it will be 0. Then first input is 1 but second input is not 0. So again it is 1. Now in reverse order, q conditional p means first 1 should be there in q, then 0 should be there in p. For such values you should write 0, otherwise all 1. See 1 0. So I can write 0 over here. 0 means let write 0 1 is 1, 1 1 is also 1. Now not p conditional not q. So let us consider these two, not p and not q. 1 0 should be there, then only 0. 1 0 is there, you can write 0 here. Remaining positions 1 1 1. Now in reverse order, not q conditional not p means 1 should be there in this column, 0 should be there in this column, then only 0, otherwise 1. 1 1 is 1, 0 conditional 1 is 1, 1 conditional 0 is 0, then 0 conditional 0 is 1. Now from this table you can you may observe that p conditional q, this column, and not p not q, the last column, both are logically equivalent. That is, truth values are same, 1 1 1 1 0 0 1 1. So truth values are same. So from this truth table we can have one standard result called this one, that is p conditional q and its contrapositive are logically equivalent. So this is nothing but contrapositive of p conditional q. So both are logically equivalent. Now one more observation is q conditional p and not p conditional not q. These values are same. See here 1 1 0 0 1 1 1 1. So both are logically equivalent. So second standard result or condition standard result we may get is q conditional p is logically equivalent to not p conditional not q. That is, converse and inverse of a conditional are logically equivalent. Okay. Well, now in future you can use these standard results. Now let us try to understand what is logical implication. So it is denoted by the symbol, see, arrow mark with double lines. Now here it means that P implies Q. It is read as P implies Q. If P doesn't imply, then it is symbolically represented as this. P not implies Q. What do you mean by this? So if P is true, then only Q is true. It means that P implies Q. If P is false, then Q is false. So if at all you want to Q to be true, then P must be true. So the P implies Q can be read as P implies Q first. It can be written like this, and we can read it as P is sufficient for Q or Q is necessary for P. All these three statements are same. I am repeating it. P conditional Q means, sorry, P implies Q means P is sufficient for Q, or we can also say that Q is necessary for P. So this is logical implication. We will use it in further examples. Well, now what kind of examples we may get on the concepts called as converse, inverse, contrapositive and logical implication? Let us see. The first example would be like, write down the contrapositive of this statement with only one occurrence of the connective, this conditional, and no occurrence of the connective, this one. So before we solve this, let me write one standard result again. If we have P conditional Q, then it can be written as not P or Q. I hope you remember this. If not, please try to remember this statement. It is a standard result. P conditional Q can be written as not P or Q. So using this, let us try to solve the first example. So what is the given? P conditional, Q conditional, R. Now we should write down the contrapositive of this statement. Contrapositive of this statement is nothing but if it is a P, it is a Q, then it will be not Q conditional, not P. That is the contrapositive. Not. So this is our this entire thing acts like Q. So not Q conditional R conditional this it's not P. Okay, so this statement is contrapositive of given. Now we have written contrapositive of the given statement or given proposition, but we should represent this statement or contrapositive in terms of the proposition which has only one connective, but here in this statement there are two connectives, 1, 2. So we should remove or eliminate one of these two. So let us try to solve. Now I said I can write, if P conditional Q, I can write it as not P or Q. So this entire thing, let us assume it as P and this not Q as Q. So and it is of the form P conditional Q. What can be written for this? Not P or Q I can write. So not P, not P. P means here this thing, not Q conditional R, or Q. Q here means not P, not P. Now we have written in terms of only one connective. So it can be further solved like Q conditional R, because this negation of negation will be the same thing, or not P. So what I can say is this is the first required result, that is A. We have represented it only one occurrence of connective conditional. So there is only one occurrence. Yes, we have eliminated that first one. Now let us try to solve even this. Then it will be, now Q conditional R can be written as not Q or R, or not P as it is. Now this is the second required result, that is with no occurrence of the connective. So this example is completely solved. Well, one more type of example may appear like, prove the following: P and P conditional Q implies Q. It is not logically equivalent, remember, it is implies. So in such cases we should go for plotting or writing truth table. Now let me write truth table for the same. So I will consider P, then Q, then we may need not P, then we may need not Q, P or Q, then P conditional Q. These are the possible values. So 0 0 1 1 0 1 0 1. Well, not P means negation of P. I should write 1 1 1 0 0 1 0 1 0. Now P or Q, P or Q means whenever we have both zeros there should be 0. P or 0 or 0 is 0, remaining all 1. P conditional Q means 1 0, if there is 1 0 then 0, otherwise 1 for all. Now from the truth table, say whenever we have P this and P conditional Q as true, then it implies that Q is also true. So let us try to see. Here 0 0 0 and 1 is there. Where is Q? Q. It is 0. No. Yes. Then P is 0. 1 is, sorry, P conditional Q is 1. So it is not implying. It is 0. Now whenever P, here P is 1 and P conditional Q is also 1, then Q is 1. Now from the truth table we have proved this first statement. That is, whenever P and P conditional Q both are 1, it implies that Q is 1. You forget about remaining combinations. You should only concentrate on whenever P and this P conditional Q is 1, in that case whether Q is 1 or not. That is the only concern. Well, similarly for the second, P conditional Q and not Q. Where is P conditional Q? This one. And not Q should be 1. Where is not? Yes, here. Not Q is 1. P conditional Q is 1. In this combination, whether not P is 1? Yes, it is not P. So hence it is proved that whenever P conditional Q and not Q are true, it implies that not P is also true. Thank you.